Examples on sets relation and function. Let Z be set of integers and for AB belongs to Z, there exists a relation between, define a relation A related to B if and only if 3 divides A minus B. Show that the relation is equivalence relation, and hence find all distinct equivalence classes. So the step number first, symmetric. Now since 3 divides 0, this implies 3 divides A minus A for every integer A in Z. So this implies A related to A for every integer A, and therefore a given relation is a reflexive relation. Reflexive, not symmetric here. Reflexive. Step number 2, symmetric. Now if A related to B, then 3 divides A minus B. This implies A minus B is multiple of 3. So this implies A minus B is equal to 3k or some integer k. But this implies B minus A, if you multiply both sides by minus sign, then B minus A is equal to 3 times minus k. Okay, this implies 3 divides, that is B minus A is multiple of 3, and this implies 3 divides B minus A, and this implies B related to A. So if A related to B, then B also related to A. Since A related to B implies B also related to A, and therefore given relation is symmetric. Now next, number 3, transitive. Now if A related to B and B related to C, we want to show that A also related to C. Now since A related to B implies 3 divides A minus B, and B related to C implies 3 divides B minus C. So this implies this A minus B is A minus B and B minus C is multiple of 3. These numbers are multiple of 3. So this implies A minus B is equal to thrice K1 and B minus C is equal to 3 times K2. So this implies Now if we consider here a minus c, we can write this a minus c as a minus b plus b minus c. Then the value of a minus b is equal to 3k1 and the value of b minus c is equal to 3k2, and therefore this implies a minus c is equal to 3 times k1 plus k2, and this implies this a minus c is multiple of 3, and this implies 3 divides a minus c, and therefore this implies a related to c, and therefore if a related to b and b related to c implies a also related to c, and therefore this implies the given relation is transitive relation. Now since step number 4, since the given relation is reflexive, symmetric and transitive, therefore this implies the given relation is an equivalence relation. Now next step number 5, we want to determine equivalence classes. Now the equivalence classes of, say, x bar is equal to collection of all y such that x related to y. So here if you start from 0 bar, then the 0 bar contain all collection of all x or y such that which are related to 0 bar, so which is equal to -6, -3, 0, 3, 6, 9 and so on. All these numbers are related to what? 0 bar, because their difference with 0 is multiple of 3. Next, 1 bar is equal to, now we want to determine all these numbers such that their relation with 1 is equal to what? Relation with 1 that is the all such x is that their difference with 1 is multiple of 3. So -5, then -2, -1, what, -1 is -2, so take 1, not -1, 1, then 4, 7, 10, all these numbers are numbers are related with 1. Next, 2 bar is equal to -4, -1, 2, 5, then 8, 11 and so on. So all these numbers, their difference with 2 is what? Is multiple of 3. What is 11 minus 2? 3, and which is multiple of 3. Next, if you try to find the 3 bar again, then 3 bar is nothing but the 3 bar which is equal to again -6, -3, 0, 3, 6, 9, 12 and so on, which is same as 0 bar. So the distinct equivalence classes is what only, and therefore the equivalence classes are 0 bar, 1 bar and 2 bar. Next, example number 2. Let f is a function from set of real numbers to R to R, and defined by f of x is equal to thrice x plus 4, show that f is bijective, and also find the formula for f inverse. So the given f of x is equal to, when we said f is a bijective, f is 1 1 injective and surjective, that is f is step first, f is injective, that is we want to show that f is 1 1. So consider here f of x is equal to f of y. To check whether it is 1 1, consider f of x is equal to f of y. So what is f of x? It is thrice x plus 4 is equal to thrice x plus y, thrice x plus 4. Thrice x plus 4 equal to thrice y plus 4. So this 4 will get cancelled here. It is thrice x is equal to thrice y. Okay, this implies this 3 will get cancelled here, and x is equal to what? Y. So f of x is equal to f of y implies x is equal to y, and therefore f is injective. Now next we want to show that f is surjective, that is step number 2, f is surjective. That is f is onto. That is we want to determine for, let x belongs to, that is we want to show that for any y belongs to R, there exists x belongs to R such that f of x is equal to what? F of x is equal to what? Y. Or so here f of x is equal to what? Thrice x plus 4 is equal to what? Y. So this implies we want to solve this equation in terms of x. So thrice x is equal to y minus 4. This implies x is equal to y minus 4 divided by 3. So if we take here x is equal to, y minus 4 by 3, then f of x, which is equal to f of y minus 4 divided by 3, is equal to 3 times y minus 4 divided by 3 plus 4, which is equal to this 3 will get cancelled here, and y minus 4 plus 4 is get cancelled here, is equal to y. So if we take any y from here, if we take any y from codomain, there exists x. What is x here? X is equal to y minus 4 by 3. That's such that f of x is equal to y, and therefore f is onto. F is what? Surjective. F is surjective. And what is your x? X is equal to y minus 4 divided by 3. Now next, since f is 1 1 and onto, step number 3, f is injective and surjective, therefore this implies f is bijective. Next we want to determine f inverse. Step number 4, we want to determine f inverse. Now here, since f of x is equal to y, from step number 2 we can write, since f is 1 1 on 2, therefore f inverse exists. From this we can write f x is equal to f inverse y. And what is x here? From this, x is equal to what? Y minus 4 by 3. So here y minus 4 by 3 is equal to f inverse y. So the inverse function is what? F inverse y is equal to y minus 4 by 3. If you write the given function in terms of x, we get the f inverse x is equal to x minus 4 divided by 3. So this is the formula for f inverse. Okay, from this equation, if we change, instead of y, if we write x, we get the formula for f inverse. So so the f is 1 1 on 2, and we find the formula for f inverse. Example number 3, let f is a function from real number set to real number set, and g is also function from real number set to real number set, defined as f of x is equal to twice x square plus thrice x plus 1, and g of x is equal to twice x minus 3. Find the formula for find the composite function f o f g o g f o g and fourth g o g. Now here composite function exists because the all these composite function exist, g of g or f o g, g o g, g of f, because here the domain and codomain of f and g are what? Same. So first, if we try to find f o g, that is a third number, then it is f o g x is equal to f of g of x, which is equal to f of g of x is equal to twice x minus 3, and if we put in the here in place of x, if we put twice x minus 3, we get twice x minus 3 bracket square plus 3 times twice x minus 3 plus 1, and therefore we know that what is a minus b bracket square, it is equal to a square, that is twice x square, it is 4x square, multiply these two terms, so it is 6x minus 6x multiply by 2, so minus 12x plus 9 plus 6x minus 9 plus 1 here. So this plus 9 minus 9 will get cancelled here, and answer is what? 4x square minus 12x minus what here? 12x it is equal to 4x square minus 12x plus 6x, it is minus 6x and plus 1. So this is what the formula for f o g. Next we want to determine the formula for g o f. So g o f of x is equal to g of f of x, which is equal to g of what is f of x? F of x is equal to x square plus thrice x plus 1, x square plus thrice x plus 1, and which is equal to now what is g? G is equal to twice x minus 3, so this is equal to 2 times x square plus thrice x plus 1 minus 3. In place of x we write here what is g? G is equal to twice x minus 3, so in place of x we write it is equal to x square plus thrice x plus 1. So if you multiply these two inside the bracket, we get twice x square plus 6x plus 2 minus 3. So the answer will be twice x square plus 6x minus 1. So this is the formula for g of f of x. Next, if we try to find the formula for g of g x, then it is equal to g of x. Here g of x is equal to what? Twice x minus 3. So it is equal to g of twice x minus 3. Again, what is g of x? It is twice x minus 3. So in place of x we want to put here twice x minus 3 minus 3. So this is equal to 4x minus 6 minus 3. So this is equal to 4x minus 9. So this is the formula for g of g. Similarly, you can find the formula for f o f. X is equal to f of x, which is equal to what is f of x? It is equal to x square plus thrice x plus 1 plus 1, and what is f of x? It is equal to again x square plus thrice x plus 1 bracket square plus 3 times x square plus thrice x plus 1 plus 1. So if you solve this, we get the formula for f o f. Next example number 4. Let x is equal to a b c d. X is equal to a b c d, construct an example of a relation on X. Construct example of a relation on X of each of the following type. The first type is reflexive, symmetric and transitive. Reflexive, symmetric but not transitive. So here for reflexive, we know that if every element of the given set is related to itself, then we can say that it is a reflexive. So A, B, C, and D. Now since we want it should be a reflexive, so symmetric as well. So if we consider here the next, if we consider here AB and BC, then AB and BA, AB, BC and BA and CB. Now you can check here, it is reflexive because every pair is related to itself. It is symmetric as well. The AB, then BA is also there, BC, CB is there, but A related to B and B related to C, but A related to C, so there is no pair A related to C present here in R, in the given set R, okay, and therefore given relation is reflexive, symmetric but not transitive. So this is the example of reflexive, symmetric but not transitive. Next, number 2, reflexive, transitive but not symmetric. Reflexive, transitive but not symmetric. So now we consider here, consider set R is equal to reflexive. So AA, BB, CC and DD. So each pair related to itself, therefore given relation is reflexive. Now consider here AB and BA. AB, BC and AC. So if you consider here BC, then now you can check here, the given relation is reflexive. It is also transitive. A related to B, and B related to what? C. So A related to C is also there. Again if we check here, okay, so pair is only there is one condition, B related to C, but there is no pair C related to anything. Here A related to C, but again there is no pair C related to A. So here this relation is transitive, reflexive but not symmetric. Why not symmetric? Because A related to B, but B does not related to A, and therefore the given relation is not symmetric, but it is reflexive, transitive. Okay. And then example number 3, symmetric, transitive but not reflexive. Symmetric, transitive but not reflexive. So we can construct here set R, AB, BA and AA. Now you can see here the given relation is symmetric. Why? AB is there, then B also, A his pair is also there. Now A related to B and B also related to A, so we want A also related to A. The A related to A pair is there, but the given relation is not, so it is symmetric, transitive but not reflexive. Why not reflexive? Because when we say reflexive, because if every pair is related to itself or every x in that set, so the given relation is symmetric, transitive but not reflexive. Why not reflexive? Because BB is not there in the given set R, then CC is not there, DD is not there, therefore it is not reflexive. Then next, reflexive but neither symmetric, not transitive. Reflexive but neither symmetric not transitive. So the given relation should be a reflexive. So we want a pair AA, BB, CC and DD. And now consider AB, say BC. Now the given relation, you can check this relation is reflexive. Why? AE, BB, CC, DD pair is belongs in the given set R, but A related to B and there is no pair B related to A, or the pair AB lie in set R but BA is not there, therefore it is not symmetric. Again, A related to B and B related to C, but there is no pair A related to what? C, and therefore the given relation is not transitive. So the given relation is what? Reflexive but neither symmetric, not transitive. Now the next example number 5. Symmetric but neither reflexive, not transitive. Symmetric but neither reflexive, not symmetric. Neither reflexive nor transitive. Symmetric but neither reflexive nor transitive. Now here the given relation should be symmetric, so consider AB, BA. Okay, now if you consider this set AB and BA, this relation is symmetric. You can check here, A related to B, then there is also B also related to A, so it is symmetric. But since AA is not, the pair AB does not belongs in set R, therefore it is not reflexive, as well as it is not transitive also. Why? Because A related to B and B related to A, but A does not related to A, and therefore the given relation R is symmetric but neither reflexive nor transitive. The next example number 6, transitive but neither reflexive nor symmetric. Transitive but neither reflexive nor symmetric. So the given relation R is equal to, consider set R, AB, BC and AC. Now you can check here, A related to B, B related to C, and then A also related to C. Okay, again B related to C, but there is no C related to A related to C. So you can check here, this relation is transitive. This is what? Transitive. But it is not reflexive. Why? Because the pair AA, does not lie in the given set R, does not belongs in the set R. Again, A related to B, but B does not related to A. The pair, there is a pair AB in a given set R, but there is no pair BA in the given set R. Therefore, it is not symmetric as well as it is not reflexive. And last one, which is neither reflexive nor symmetric nor transitive. Not reflexive, not symmetric, that is neither reflexive nor symmetric nor transitive, not transitive. So now consider the given relation R is equal to AB and BC. Just this set AB BC. You can check here, it is not reflexive. Why not reflexive? Because the pair AA, AA does not lie in the given set R, therefore not reflexive. Not reflexive. Again, you can check here, A related to B, but B does not related to A, and therefore not symmetric. Again, you can check A related to B and B related to C, B related to C, but A does not related to C, and therefore the given relation is not transitive. Is what? Not transitive. So you can check, it is reflexive, it is not neither reflexive nor symmetric nor transitive. Now the next example, the last example, example number 5. Find domain and range of f of x is equal to x square minus 1, and first example, and B f of x is equal to x square plus 1. Now we know that this function, first A, f of x is equal to x square minus 1 is defined for every real number x. It is defined for every real number x. Therefore, domain is equal to minus infinity to plus infinity, or in other words, you can write it is a set of all real number. Now, what is the range here? The range is equal to, now if we draw the geometrical representation of the given function f of x is equal to x square minus 1, this is the x square minus 1, so here is the minus 1. So, or you can, in other words, you can check here, f of x is equal to x square minus 1. For 0, f of 0 is minus 1, f of 1 for f of plus or minus 1 it is 0, f of plus or minus 2 it is equal to say 3, and so on. So what is your range? It is minus 1 to infinity. Or you can check here, this part is represent the range, okay, y-axis represent the range, and therefore range is what? Minus 1 to infinity. And the second example, f of x is equal to x square plus 1. Again, this function is defined for every real number, so the domain is minus infinity to plus infinity, and range is equal to, again if we draw its geometrical representation, then this is the graph of x square plus 1. You can check here, the range is what? 1 to infinity. 1 to infinity. In other words, what is f of 0 here? F of 0 is equal to 1, f of plus or minus 1 is equal to 2, f of plus or minus 2, or and so on is equal to what? It is 5, and so on. So the graph is what? It is from 1 to infinity. The y-axis is from 1 to infinity, and therefore range is what? 1 to infinity.